I'll be talking about multi-constraint and multi-objective material optimization. Okay, so this is basically a continuation of what we started last week, and then hopefully we'll do a few examples in your lab sessions this week, and then that will allow you to apply this on your project, which you have already been assigned. So uh, for the further reading, again, it's primarily from the same source, but now the focus is more on chapter 7 and 8. So in the last week, it was more on chapter 4. So you can again read this from the same link. So today, our main learning outcome is to explain the formal process of multi-objective and multi-constraint optimal material selection in context of machine design. Now, to begin, I would like to revise what we discussed last week, right? So with certain examples, I said that the first thing is that you do the translation, you try to understand what type of mechanical function or other function is being performed, and based on that function, you define a set of constraints that must be met, right? And those constraints can be will need to be specified in terms of different material properties. And I'm giving you a general sort of a list of typical constraints. So for example, you can have a constraint on the minimum expected value of Young's modulus, minimum expected value of yield strength, thermal conductivity, maximum service temperature that you're expecting for your object, corrosion resistance properties, and then even things like manufacturability or ability to be molded in that particular shape. Once you have a list of candidate materials that pass all of these criteria, what you need to do next is to rank them, right? And that ranking is based on a certain objective that you have defined as part of your translation. So in this case, I've given you the example of the cost, and basically once you do this and apply this on a software like CES, you end up getting a list of candidates which are then ranked, and you've got the best candidates here in the bottom of the screen. Now that's pretty straightforward, isn't it? Yeah. But what we discussed last time was that this is applicable if almost everything is fixed in your design, right? You are at that detail level where perhaps the only free variable is material selection itself, right? And all the other things are fixed and they are your constraints. Then you can apply this approach very easily like this. But if you are at a different stage of development, like for example, if you are in embodiment level, right, a lot of variables are still free. You are able to choose, for example, in certain cases, the diameters, and that may lead to then choice of your area. You may be able to choose, for example, change, for example, the length to certain extent, right? Even if you are saying that it is fixed based on a certain configuration, you may have certain flexibility in your design. Now, if you are operating at that embodiment level, right? So I hope you remember, right, the diagram that I showed you. The 4 stages: the conceptual design, embodiment, detailed design, and then prototyping. So I'm talking about the second stage where we are at the embodiment level, right? So now, basically, to reflect upon this previous selection attribute that we just did for the simple case, let's try to take a practical simple example of a tie rod. Yeah. Now, of course, the tie rod is an approximation of a mechanical function that you find in so many machines and devices. So for example, a tie rod can be the physical tie rod in a car, or it can be simply a rope that is being used for pulling a tow truck, right? Because that's basically an axial member in tension, isn't it? Or it can be one of the other members in any machine that is basically transmitting the axial load. So for that kind of a tie rod, often the constraints are on strength, but at the same time there may be some constraints on deflection. And when we talk about machines, many times it's actually you have already designed the structure with a certain factor of safety, so you're already trying to keep the stresses low, but you can't even tolerate a little bit of extra deflection because that causes misalignment, right? And those cases, the deflection constraint or the can be more important for you. In other cases, the strength constraint may be more important for you because a little if you go above the certain limit, you may end up with a catastrophic failure, right? That can then result in loss of life and other things. So different scenarios and different components require that as an engineer you give importance to different constraints, more important to different constraints as opposed to other. Now, let me explain what the problem is. So, if for this tie rod you have two constraints, one constraint is on the deflection, right, that how much it can deflect, and the other constraint is based on the maximum load that it needs to bear. Now, if let's say for argument's sake your objective is to minimize the mass of the object, right, mass of this tie rod, right? Now, you can write down your mass equation just like we did last time, when we were deriving the material indices. I showed you the derivation last time, and then I left you with the video to watch to actually how to plot them, right? But let's say we have the same objective of minimizing mass. Now, the mass equation is the volume times density, which here is expressed as area into length into density. Now, at embodiment level, let's say we are still free to choose our area, right? If we are free to choose our area, we can express our stiffness, which is the spring constants essentially, in terms of E, which is the Young modulus material property, A and L. So when we substitute this back into the mass equation, we end up with a material performance equation, which is basically now written in terms of the constraint variable, which is the length squared into S, which is the stiffness, and then your material index density over E. Note that in this case I have kept the material index in a minimization format for consistency. Okay, so right now your performance equation, therefore, if you want to optimize this material selection with regards to the deflection, would be basically L square S into density over E. Okay, now on if you with the same objective of minimization of mass, now let's say you are trying to think about it from the point of view of constraint on the maximum load that it can withstand. Yeah, so that can be expressed in terms of the yield strength of the material multiplied by the area, isn't it? And let's say you don't want plastic deformation. If you want plastic deformation, you can replace this with ultimate strength. If you are thinking about cyclic loading, then this can be replaced by endurance limit. But right now we are simply considering a static loading, so, and we don't want it to plastically deform. So then the force limit is simply given by yield strength into area. Now that force limit, the area from this equation, if you substitute it back, leads to this performance equation, which is L into F into density over yield. Now this was exactly the material index that we defined last week. Yeah, so but now you have got two different material indices. One material index is with respect to the deflection or stiffness constraint, and the other material index is based on the basically the maximum force or the yield strength, right? So now you have got these two different material indices. Okay, now which of these you want to optimize, which of these you select? Now as a designer or as an engineer, you have to make this decision. And let's say I present to you a scenario. Okay, I present to you a scenario based on a certain given constraints on the length on the target spring stiffness and the maximum load that the object needs to be able to uh, carry, right, in that axial manner. So in this case, I'm saying my length is constrained to 1 meter. Okay. My spring stiffness that I need based on the deflection requirement, of course, I can work that out. So is 3 into 10 to power 7 Newton per meter. And my force is limited to a maximum value of 10 to the power 5 Newton. I'm not going to go higher than that, right? Okay. If let's say I have only a short list of candidate materials, I'm not using the full database of Granta because I want to show you some numbers. Yeah. So I have 3 materials: AISI 1020 steel, 6061 aluminum, and titanium 64. So I have got certain properties for these, which are the density, the Young modulus, and the yield strength. Okay. And then based on my performance equation, M1 and M2, I can substitute the numbers back, right? So once I substitute the numbers back into this equation, I can calculate a value of mass in each of these cases. Notice that if your objective was only to minimize the mass based on stiffness consideration, then steel is performing the best, isn't it? It's 1.12 is the lowest mass that is there. So steel would be the ideal candidate if you only had a single constraint on the stiffness, right? And the material index was simply based on that. But now, if you look at it from the point of view of the second material index, which was based on the second performance equation on the strength, then your selection actually changes, because now steel is not really a good option and it's giving you a option of 2.45 kilogram mass, and the best option is really titanium. Now, how you decide that which of these options is the best? Now, as a designer, you can choose, you can make that decision. So for example, I can say that basically I want both of my constraints to be satisfied, right? And because I want both of my constraints to be satisfied, so I'll go for the option which gives me the overall minimum mass. So I compare M1 and M2, and in this case, if you think about it, the overall minimum mass is actually 1.15. So that means actually using titanium in this application will be my optimal choice. Now, so far so good. Seems logical approach, isn't it? But there is a small limitation of this approach, because you see, we started with a given value of L, S, and F, right? Now at embodiment level, you are still doing those what if analysis. So maybe, yeah, let's say if this tie rod was for being used for an automobile, and maybe there is a bit of room of wiggle room, you can maybe change it from 1.1 to 1.5, right? Or maybe you can change your target stiffness depending on your design team's input to some other quantity, right? Do you think the material selection will change? Of course it will change. And actually that's what I have done in the next case, and I have given you some more values, because you see, your performance index also depends on these constraints. So if these constraints change, the mass value will change, and therefore the material selection will change. So basically what you will have is, let's say if you put 3 as the length, right? Stiffness target, you revise it to be even a higher value, let's say 10 to power 8. And let's say your maximum force is actually reduced because of whatever design considerations, and now it is 3 into 10 to power 4. And if you plot the numbers back into those equations, what you'll find out is that overall steel becomes the best candidate out of these 3 materials. Yes?
Can't we plot the values in a graph to visually see it easier?
Yes, we'll do that later on, but right now it's only 3 numbers, so it's just trying to give you a physical appreciation of the numbers. We'll do the graphical method later. But basically what I'm trying to do over here is I'm trying to explain to you the limitation in terms of if you actually use the performance function of the mass directly to minimize, right? And what the material index, if you're just looking at it, does is it basically decouples the geometric part, right, with the material part. Yeah. So now what you can, if you think about it, what you can do is, if you want to, let's say, plot these solutions, yeah, you can do that in even in a software like CES, for example. And if somebody has watched my demo, you may have seen I've shown there the advanced feature where you can type in manually the equation that you want, right? So you can actually go back and type this equation for M1 and this equation for M2. Of course, you'll need to use the certain constant numbers for these lengths, but then these can be left as material properties there, and you can basically plot all the solutions available in that database as your candidate options, based on mass 1 and mass 2, right? But now the problem that is there is, again, which objective is more important for you? Not really which objective, but which material index is more important for you, because which performance equation is more important for you? Is it the based on the stiffness or based on the strength? If, let's say, you really don't care and you think both of them are equally important, right, then basically you are at this stage where M2 is equal to M1, isn't it? Because now you have got, because whenever you plot two quantities on a graph, they basically represent a relationship y is equal to mx plus c, isn't it? Yeah. So basically, then if your coupling constant this is of between this M2 and M1 is 1, then you end up with the best choice being over here. So let's say, if you draw these selection lines in CES and you keep pulling it back, you end up with your best option. So this is a practical way of what you can do. But this approach is still limited, just like the solution that I showed you for 3 materials, because this coupling constant must be obtained by having specific values of the length, the stiffness, and the force, right? So those constraints have to be for a given case, okay, which is okay in some applications, but in early phases of designs you may want to even explore other possibilities so that you can actually reach a true optimal solution. So let's now look into those conditions. So basically, uh, if you see, each side of the solution, when you move away from that center line, is representing whether you are giving more importance to your mass M1 constraint or M2, right? Basically the performance equation, which one you are giving more importance. So instead of plotting the mass, what you can do is you can actually plot the material indices, because if you think about it, for a given scenario where your L and F and the stiffness is a fixed constraint, then the only things which are variable are those material indices, isn't it? So it doesn't really matter then whether for that particular set of numbers you can just simply compare this rho over E. Yeah. And then you basically, now you can define a coupling constraint between your M2 and M1, and in this case you can find the value of this coupling constant. So for example, in my case, my first performance equation, which was 7.2, and the second performance equation, which was 7.3, right? If I equate them, so this is the strength one, L into F into density over sigma yield is equal to L squared into the stiffness into density over Young modulus. If I now equate these and rearrange, I end up with basically a equation between density over sigma yield which is my M2, is equal to Ls over F into density over E, which is my M1. Okay. So in this case, this constant will be therefore called as your coupling constant, because it is allowing you to relate your one material index with the second material index. Okay. Now, if you are going to plot this on CES, you need to remember that the CES plots are log-log. Yeah. So just like I showed in that example when I was plotting those material indices, that you basically, to determine the slope of the line, you have to then take the log on both sides. So in this case as well, if you take the log of m2 and you say it is equal to log of m1 plus log of this coupling constant, that log of coupling constant will still be a constant, right? And therefore the slope over here is just simply 1 in this case. Okay. So if you therefore plot using the index function, right, the index line, and you plot a index line of 1 with the slope of 1, then that represents a trade-off or a compromise between your material index 1 and material index 2, right? So basically, then you can keep moving that and you can find your optimal solution based on those two. Okay. Now, that's about if you had the multi-constraint, which is actually easier to deal with. We still had just one objective. What if you don't, you not only have multi-constraint, but you actually also have multiple objectives? Okay. So first we will think about it purely from point of view of one constraint, but having more than one objective. So what can be different objectives? So maybe you're trying to minimize mass, but at the same time you're also trying to minimize cost. That will be a scenario of multi-objective optimization, right? Or for example, let's say it's a pressure vessel, right? And for the pressure vessel, you are trying to minimize the mass because let's say it's a lorry mounted pressure vessel, yeah? But at the same time, you want to make sure that you do not get a fracture. So basically, you will try to increase the fracture toughness as much as possible, isn't it? So now you can't put a fixed number on that, rather it will be your objective, right? So you can actually think of multiple objectives for the same problem from the point of view of the same constraint. Yeah. Okay. So in order to discuss this, I have used the slides directly from Granta, right? So these are the Cambridge slides. So I've not taken away the label. So please, I thought it was more fair if I just simply use the slides in their own form rather than putting our own headers there. So in this particular case, the word solution that I will be using has a specific meaning. So what does the word solution here means? It means a list of all the candidate materials that meet the given constraint, but they are not necessarily optimal. Okay, so let me show you that in a plot. So let's say you are now plotting your first objective. So remember, I was plotting M1 and M2, right? Now I'm not plotting M1 and M2, rather I'm saying there is a mass that I'm plotting and there is a cost objective that I'm plotting, right? So I plotted my mass and cost in such a way that it's in a minimization format essentially. So the cheapest is here and the lightest is here. Heaviest is on the top and most expensive is on the top. You can, of course, reverse the plots as well, but this is what we will use for discussion. Okay. So these material candidates that you are seeing over here have all basically met the constraints that you had in the system, right? That you plotted as minimum acceptable values, and they are all satisfying them, or maximum acceptable values, right? So they will all be considered as solutions. Okay. Now, what is a dominated solution? So a dominated solution is described as a solution which is clearly not optimal from the point of view of any of the objectives. So yeah, so for example, this one over here, right? It's not optimal from the point of view of mass because it's quite heavy. It's also not optimal from the point of view of cost because it's quite expensive, right, compared with other options. So this will be called as a dominated solution. In contrast, we'll use the term non-dominated solution for a solution that is typically optimal from the point of view of at least one objective, but not necessarily from the point of view of other objective. So right now, for example, this solution over here is optimal from the point of view of cost, but it is not necessarily optimal. In fact, it is not optimal from the point of view of mass, right? So this is now a non-dominated solution. Okay, so with this, if we think about it, all of these solutions which are on this front are non-dominated, isn't it? Because they are good solutions from the point of view of one objective, but not so much from the point of view of other objective. So basically, whenever we are trying to do optimization, we are trying to basically find a compromise, isn't it? Yeah. So because we have got more than one objective, so we have to make a compromise somewhere, right? So this front is now allowing us to make that compromise. So we call this surface as the trade-off surface. And in terms of statistics, it's actually called as a Pareto front, right? So this is basically your Pareto front, which will allow you to select the optimal solution. So your optimal solution will be one of these non-dominated solutions, okay? And what that optimal will be will depend on your management decisions as well as your design decisions. And many times it's actually more about management decisions, because you have to then decide which objective you weigh, you give more importance to, right? Yes.
So I can say that, oh, I am rich, I will choose the expensive one, but like
Yes.
something like that.
Something like that. So it basically depends on your target audience, right? I'll give you some examples to make this more clear. Right now, I'm just simply describing the process. Yes.
For the plots on the trade-off surface, they can be used where there is a priority on one of the objectives which is higher than the other.
Yes. So basically,
That's what they're used for, or-
so basically you can, it gives you clarity in terms of selection, and I'll show you how, because it will there are still many steps left in the process actually, and I will actually show you that you will be able to very clearly select that in this situation this is a better solution, and in this situation this is a better solution. Okay, so let's now proceed. If you want to do this on CES, and again in my demo video, hopefully all of this will be shown to you as well, but I'm just showing you right now in the form of the slides. So you can use the trade-off sketching feature in CES to actually sketch manually the trade-off surface. And now the solutions that are nearer the surface are basically your compromise solutions. And right now, these are, in this case, are 8 out of these 50. And choosing among these depends on how highly you value your one objective versus the other. Okay, and this is what I have already explained. But there can be another strategy to do this more appropriately, and that is many time a practical solution that you say, okay, yes, we want to mass is our primary objective, but we do have a budget limit, right? And that is a very, very practical thing to do. So you can say, yes, we can go for higher cost, but this is the maximum that we can afford from the point of view of cost. So you reformulate the problem at that stage. So you initially start the problem as with two objectives, but then later on at later stage you reduce one of the objectives into a constraint, in other words. Okay. Now this is a possible way to do, and in this case, for example, this will be your best choice, right? Because it is the minimum mass that you can have within your budget limit. Okay. Now this is possible and this is easy to do, but this is again not necessarily the optimal choice. And again, from a management point of view, you really don't have the visibility that really, was it even worth spending this much? Or maybe you could have spent a bit more and, gone to this solution, because there is no rationale there that is allowing you to see that, how you're taking that decision. So that's why in these slides we said, yeah, this is a way, but this is really in some ways cheating, yeah, because you are not really truly solving the multi-objective problem, and you're reducing the problem to a objective and constraint problem. Okay. A better approach, and again there can be other approaches as well, but this is one of the things that you can do directly through the Granta software. Okay, and that approach is use of penalty functions. Okay, now what do we mean by a penalty function? So basically we mean that we can define a function which is locally linear between the cost and mass m, right? So basically we are trying to see that, in other words, that how much changing, how the relationship between the cost and the mass is changing at each point on the graph. Now, why this is important? So let me show you this first of all. So first, let's say you have made a trade-off plot. Then you rewrite this equation, and now you are writing down the equation in terms of with m as being dependent variable and cost as being your x-axis variable. So you will have this quantity minus 1 over alpha. This is basically defining the slope, right, of the line that you'll plot on this surface. And again, for this approach to be successful, you will need to have a linear scale if you're going to apply this on the CES. So you will actually need to switch back to the linear, then plot the line, and then go back to the log scale. Okay, so now this constant alpha basically allows you on this plot. So think about it now. If I change the slope, right, of this curve over this green line over here, it can be more aligned to these solutions, or it can be more aligned to these top solutions, right? Depending on the slope alpha, you can decide which option is better, right? So now the question is, okay, we can read the lowest value of z based on the given value of alpha, but how do we decide that what this alpha should be? Okay, so now we have tried to reformulate the problem in form of a mathematical question, that okay, now we know how to find the solution, best optimal solution, but then how we should find this alpha. So I will explain this, and second thing will be that how we plot this linear function on a log scale, because that's more of a practical issue with the way graphs are being plotted on Granta software, right? So I'll answer both of these questions. So, but first I will focus on the question about the exchange constant alpha. And I'll again go back to my bicycle example. Okay. The graph over here is showing you for a certain bicycle, a certain set of materials. Of course, we understand that not all the components in the bicycle will be made from the same material, but right now this is just like a representative figure that I've given you. Okay. Now on this graph, you can see there are certain titaniums which are over here. They are quite pricey. Now please keep this in mind that now I'm plotting my price on the y-axis and the mass on the x-axis. Okay, so instead of having the exchange constant minus 1 over alpha, it is, in other words, basically now alpha if you compare it with the previous equation, right? So in this case, you have got the CFRPs over here, which are with this purple and the black, and then the aluminum alloys, which are over here somewhere, and then steel alloys are here spread along this, and then you've got plain steel. Okay, now once you have put your trade-off surface, then these candidates are all your non-dominated solutions. Now each value of alpha will give you a different line. So for example, if you plot the one value of alpha, you have got this line over here, right? For this, the value of alpha is $200 per kg, right? But for this one over here, the value of alpha is $20 per kg. So if thinking about it, you can try to think about it in this way, that to get 1 extra kg reduction in mass, if I am choosing, if I am in this range, okay, I will have to invest $200 more, isn't it? Because it's $200 per kilogram, right, of mass saving. So that means as we are reducing the mass, so if our absolute mass, we were saying we are happy with the 15 kilogram mass, right? To reduce from 15 to 12 or 14 to 12, the investment that you have to make is going to follow this trajectory of 20 per kilogram. But if you want to reduce the mass from 10 to, let's say, 6, or not even 6, 10 to 9, you'll have to invest 200 per kilogram. That's how the relationship is changing. So now the management has clarity that what is my target audience? Is spending 200 per kilogram really worth it? Maybe for an Olympian, yes. If your prestige is at stake and you're going to win a complete brand by doing that, so why not? You maybe want to spend that, right, and gain that market share. But if you're designing this bicycle for an average teenager, then obviously it's not going to make sense for the management, and it's a mass produced item. You would want to stay here with these as your best options, right? And that's basically how this selection methodology gives your management a way to deal with this multi-objective material selection. Now, the value of alpha, therefore, depends on the system that you are looking at, okay? And a lot of time you need basically a lot of knowledge about the overall system, and you need the knowledge about the various things. Sorry, I guess the slide just simply went forward. So so you need to have an appreciation of what is your target again. So let me give you another example here. So whenever we talk about mass savings from the point of view of transport systems, there are two things that we are thinking of. One is the actual reduction of the physical mass of the vehicle, but then there is also a fuel cost associated with that vehicle, right? So for example, so basically your life cost will be some initial cost which will be related to the choice of material that you're making and how much mass you are reducing, but then there will also be a fuel cost related with mass in terms of the kilogram that you will save for every run of that vehicle or that transport system. The penalty function, of course, is again being described in the same way, with this being described in terms of dollars per kilogram. But if you are trying to reduce if you're trying to think about mass reduction from the point of view of a commuter car, right? Initially, you make the commuter car very light, for example, yeah, but will that make a huge difference over the lifetime of the vehicle? Not so much. Why? Because what will happen is that because the commuter car, the amount of fuel that you burn, right, is relatively small if you compare it with, for example, a jet engine, right, or a spacecraft, right? So the amount of fuel that you are going to save by making it light is quite small, right? And similarly, you may make the actual vehicle small, but then there may be an extra passenger which will just simply offset whatever advantage you got. Yeah. So what I'm trying to say here is that if you try to work out the exchange constant for these kind of scenarios, typically the exchange constant for a commuter car comes to be around 3 to 6. For a transport vehicle, it's actually, because now it's transporting heavy goods and it's much bigger in size, you're talking about 6 to 20, and the material choices change accordingly. For a commercial aircraft carrying passengers, it's in the range of 100 to 600. And for a jet fighter, it's between 600 to 2000, obviously depending on your performance requirement. But for a space shuttle, it's way high. It's up to 5,000 to 10,000. So basically, that then tells you that in these applications, moving from this site to this site, here saving mass is the most important objective, whereas here saving cost is actually a bigger objective. So basically, this is how the exchange constant uh, helps you decide between different design options for the material selection. Now, to actually plot this exchange constant on CES, what you'll need to do is, first of all, you'll convert the graph to a linear scale, then go on to the index line feature, right, that I showed you in the demo, and I'll again show you later on with the practical demo as well. So, and then you convert the graph. If you convert the graph back into a logarithmic scale, your initially, which is appearing as a linear line, will appear like a curve. And because then that curve can be pulled down, and whatever is the lowest point on that curve will represent your optimal solution based on that value of alpha, because you have to plot it for a particular value of alpha based on your system. So I think with this, I can actually stop at this point. So because I will continue this discussion, I have a case study to cover in the next lecture, which I will cover in the Wednesday lecture session. That is about the choice of materials for the car bumpers, and hopefully we'll continue the discussion then. Okay, thank you.